אורלי, קודם כל אני רוצה להודות לאור ירוק וציפי לוטן שהזמינו אותי להשתתף בכנס הזה ולדבר עם קהל כל כך מכובד. זה תמיד תענוג בשבילי להיות שוב בארץ, ואתם יודעים שיש הבדל בין נהיגה אוטונומית ומכונית ללא נהג. אני הסברתי מה זה מכונית ללא נהג לאשתי לפני שנתיים, והיא חשבה רגע וענה, מה זה מיוחד בזה? כל זמן שאתה מוסיף אותי, אני מרגישה שאני במכונית ללא נהג. אז עכשיו אני אעבור לאנגלית, יהיה קצת יותר קל בשבילי להמשיך. The Media Lab at MIT has a project called Automotive, and the project is to develop technologies that will sense the emotions of the driver and change the environment and the way of interaction in the vehicle to make it more, or to enhance the human experience, as it were. And we can imagine how this is going to be transforming the vehicle of the future. למשל, בבוקר אני מזמין מכונית ומכונית מגיע מיד, ואני נכנס ואני שומע, בוקר טוב יחיעם. המכונית מכיר אותי ומכיר את השם שלי בעברית, ואני שומע, הפגישה הראשונה שלך הבוקר זה בשעה 9. ואני רואה שאתה קצת עייף, ואני התחברתי עם המיטה שלך, וכפי הנראה שלא ישנת כל כך טוב אתמול, אז אני מייעץ שבדרך למשרד הכל מוכן בשבילך, יש זמן, אנחנו נעצור בארומה ואני אזמין לך כוס קפה, אני חושב שקפה טורקית יותר מתאים למצב שלך. בינתיים תשב, תנוח, אני אשים קצת מיוזיקה קלה ויוריד קצת את הטמפרטורה והכל יהיה בסדר, אל תדאג. אני מייעץ שתסתכל בעמוד 4 של הדוח שלך, כי זה העמוד הכי חשוב. יפה, נכון? There are other scenarios that are not quite as rosy as that, and how these scenarios will come to fruition will depend very much on the nature of disruptive changes that are going on at the present time. For example, the technology industry is pursuing mobility, which has been traditionally a domain exclusively used by automotive manufacturers, but we see more and more technology companies getting into this space. The vehicle of the future will be a digital platform, not a mechanical platform as we know it today, and this will change dramatically our experience with the automobile of the future. And car ownership, mobility will not depend on car ownership. The shared economy is going to provide many more alternatives for getting around than having to own a vehicle. So what is automated driving? Well, it's really a situation where the driving task, or at least part of it, does not require direct input by the driver. And many people believe that this will have dramatic safety benefits. For example, we know from over 30 years of research, and David Chinau is one of the pioneers of this, that driver error accounts for between 70 and 90% of accidents. So the calculus is that if you eliminate driver error, you'll have a dramatic reduction in accidents. We can all subscribe to the Volvo Vision Zero concept, but it's not quite as simple as that. זה הכי קל להאשים את הנהג, אבל זה לא כל כך פשוט. There's two things that I want to highlight. One is that driver error is essentially reserved for a category of crashes where the crash was not, did not involve mechanical failure or an act of God. Almost everything else falls in the category of driver error. The other thing is, as we heard from other speakers this morning, crashes are very rare events. And so when we get into the realm of automated driving, we know that the distribution is going to change, but we don't necessarily know that the absolute number of crashes is going to change. Hopefully it will. We know that computers are faster, they're more precise, and they're more consistent. They don't drink alcohol, they're not affected by circadian rhythm, they don't get old, and they don't get sick. Some of them may have viruses every once in a while, but generally speaking, they're more reliable than humans. A recent study published 2 months ago by the Virginia Tech Transportation Research Institute reported on the crashes that involve the Google car. This is a driverless vehicle. As you can see, the statistics that were published in this report. The Google car was actually involved in 8.8 crashes per million miles traveled, whereas traditional vehicles were involved in about 20 crashes per million miles traveled. So there was a reduction, but you must also remember that the Google car only drives in autonomous mode under ideal conditions. Under other conditions, the driver needs to take control. And so this crash rate is only for the vehicle crashes in autonomous mode. We might have expected a much lower accident reduction than that. The good news is that the majority of the reduction is really in the most severe accidents. And we can imagine that this is the first version driverless vehicle. In the future, we expect that the reduction in accidents will continue. But we also know that the software industry standard is 25 defects per 1,000 lines of code, programming code. And so it's not entirely clear what the impact will be on the accident rate in future vehicles. This brings us to the question of trust in automation. And this is a topic which is really relevant and important when we talk about driverless vehicles. It's not something I'm going to speak a lot about this morning, but in the realm of aviation and the process industries, this has been studied for years, and there's a rich literature on this. And many scientists have developed models for understanding more clearly what determines human trust in automation. And just as important, something that we don't hear much about is the need for society to have trust in institutions. So I'm talking about the private industry, the automotive manufacturers. The public needs to have trust that the manufacturers will exert best effort in developing technologies. They must have trust in governments that they have the resources and the instruments to safeguard the public safety, not only to invest in promising technologies, but also to make sure that the technologies that are brought into the roadway are safe. And finally, there needs to be trust that academic institutions will do credible research to help inform private industry innovations and also public sector policy making. These three sectors need to work together because in the future, we're not going to just have a Volvo vehicle or a Google vehicle. We're going to have Volvo vehicles, Google vehicles, Apple vehicles, General Motors vehicles, then they all have to be able to interact and navigate in the same space. And so there needs to be some common understanding, common infrastructure for that to happen. To sum up the trust issue, a report that just was produced last month by J.D. Power, which is a major research information service, basically concluded on vehicle dependability, and I'll quote from the report, "Right now, if consumers can't rely on their vehicle to connect to their smartphones, they're certainly not yet ready to trust the autonomous technology will keep their vehicles out of the ditch." And this is the current state of affairs. Hopefully things will improve, and my talk is going to be about how things should improve as we go forward. So let's look at automated driving a bit more closely. NHTSA, the National Highway Traffic Safety Administration in the United States, and the Society of Automotive Engineering came up with definitions of levels of automation. And you'll see them here. I'm not going to go into details, but both of them have 5 levels of automation. I don't believe that these are very useful. One, because they do not establish design requirements or help designers make design trade-offs and help them design technologies. They do not help regulators and the public to adequately understand the capabilities and limitations of technology. And they do not inform industry and consumers about training needs. And as we get into more of these high technologies, we're going to need to have a lot more emphasis on training, virtual training, and so on. Instead, what I think is more useful is to look at autonomous driving in terms of 2 dimensions. One is, are we talking about partial automation, or are we talking about complete automation? The meaning is it technology that is going to assist the driver, or is it technology that is going to replace the driver? And the second dimension is this technology going to be operating all of the time or part of the time? And so if we look at this as a matrix, we have 4 quadrants. The first quadrant is well established. The second quadrant is also fairly well developed. The third quadrant is nascent. It's just starting to come about. And we saw the Volvo films earlier, which is about autonomous driving for part of the time. What we don't see, and what is almost non-conceptual at this stage, is really quadrant 4, which is complete automation all of the time. And there's a lot of confusion between quadrants 3 and 4, because a lot of people who talk about autonomous driving seamlessly talk about it as if it's autonomous driving all of the time, but really and truly it isn't. It's very hard to conceive of a vehicle that can navigate downtown Tel Aviv or Boston or anywhere else, given the uncertainty and the complexity of the environment, which is constantly changing. So if we look at only the 3 quadrants that really are going to be operating in the foreseeable future, what do they have in common? Basically what they have in common is they all involve the driver in some capacity. It's only the 4th quadrant that has no driver involvement. And this is very important because the development of technology depends very much on the existence of the driver. And in fact, if you want to develop safety and innovation, they sometimes conflict. I'll give you an anecdote. When I was responsible for motor vehicle safety standards and regulations in Canada, I proposed something which was very novel, which is to regulate the process of developing technology. If I knew that the process of developing technology involved due diligence by competent people and that the results of tests are going to be implemented in design, I would be willing to accept whatever final product would result, because I knew that as a regulator, there's no way that I could regulate the final product. By the time I got around to it, the final product will be changed. It will be different. It will be something different. And so the only way that I could get ahead of it was really to regulate the process of design. But I had a lot of opposition from the OEMs, the original equipment manufacturers, as well as other governments. And on one of my trips to Japan, I was invited to a private banquet at one of the major manufacturers with a senior executive. And so I took the liberty of asking him, maybe chutzpahdik like this morning. And I said, so why would your company object to this? You are so well developed. The process that I envision, you already follow. And the regulations would essentially give you competitive advantage over the industry. And he basically said something to me which was quite remarkable, which is, we don't want to stifle innovation. We want to have the marketplace decide what is successful, and we will simply buy the technology. Well, unlike this executive, I don't believe that we should use the roadway to do our test and evaluation and trial and error. So we need to find a way in which safety does not stifle creativity and technology does not do any harm. So when we're talking about involving the driver, we need to address some ironies of automation. These come from aviation, process industries, and so on. And the reason they are ironies is because while technology is supposed to relieve the driver, in actual fact, in many cases, it actually encumbers the driver even more. So for example, the driver is allocated tasks that are too complex or unusual to automate. Lack of practice leads to diminished skills and situation awareness. The driver must monitor a system that is highly complex and without situated mental models or diagnostic skills. The driver requires better knowledge of system dynamics, not just the vehicle, but the entire system. We know from military uses and so on that automation can only enhance the driver skills and knowledge if it is accepted, trusted, and used appropriately. And finally, because I come from an insurance company, I need to add the fact that the driver retains responsibility to avert the crash if it is at all possible to do so. So far we've concentrated on the autonomous vehicle, but we know that in the future the vehicle is going to become part of the Internet of Things. And the Internet of Things will connect the vehicle, will connect the smart city, the smart home, the shared economy, and so on. And so we are no longer dealing just with a driver, we're dealing with a whole lot of other people who are going to be part of the overall system. This is a concept map of cyber-physical systems. I see that my time is running out, but I just want to, this is some statements that were made by, this year's TRB by Ed Giffer, who is from the National Institute for Standards and Technology. He's a physicist, and he says, we lack the science and technology to conceptualize and design the deep interdependencies among engineered systems and the natural world. Very important, we don't know how to provide software security. And we are in trouble if the technology is discrepant with user mental models. So, as I mentioned, we're not just dealing with the driver, we're dealing with a whole lot of other people who are part of the system, and we need to start taking that into account. And so this brings us to look at the whole driving situation, mobility, from a socio-technical perspective. And a socio-technical system really is a combination of organizations, technology, and people to achieve a common aim. And if you look at it from a hierarchical standpoint, there are layers of control and feedback loops. Each layer comprises social, technical, and organizational systems. And the safety of the system is an emergent property. You can't look at any simple part of the system and try to solve its problems because it misses the interactions that are so critical in determining what the safety outcomes of the system must be. So I'm not going to go through this. I wanted to say a bit more, but if you look at a socio-technical system, there are many elements that are involved in it, as I say, not just the driver. And we're going to need to look at each element and design that element using a human-centric approach. And at the human system interaction level or integration level, we need to make sure that we can resolve all the trade-offs and competitive requirements within or among those requirements. This all needs to live within the transportation system planning, where we develop the regulations and laws, the safety culture, and so on. And finally, this leaves the broader ecosystem, which is determined by social, political, and economic criteria. All of these things infringe in the design of the socio-technical system and must be taken into account. So in closing, I want to summarize by 3 key messages. It's not just about the driver, it's about all the people in the system. It's not about designing the human interface, it's about creating value and trust. And 3, it's not just about driving, it's about mobility in the Internet of Things. And I think if we're going to develop trust in automation, there are a number of needs and opportunities that we really must pay close attention to. One is public and private sector must develop a common human-centric socio-technical systems architecture at the pre-competitive level so that everybody understands what the rules of the game are. We must advance the relevant neurosciences, the cognitive behavioral sciences, to support mental models, situation awareness, and responses, as well as training strategies. And finally, we have to test all of these modes of operation, not only the system design, but also to make sure that when the system operates, it operates according to design and adjustments are made in order to be able to develop the trust in automated systems for the future. So my time is up. Thank you very much for your attention. I appreciate the opportunity to be here.